All right, friends and neighbors, welcome back to another networking video. Previously, we did subnetting examples, and we did a Class C and a Class B subnet example. Right now, we're going to do supernetting examples. And do you see how I put the ones and zeros underneath the supernetting? Because super is, anyway, there we go. Subnetting previously, and now supernetting. All right, so we got to remember, right? Class full addressing. There's our classes A, B, and C, and there's our default masks. Now we got to remember that this is how we started. It's not how we do things today. Very, very wasteful. And because of that, we chop up the mask. We make subnets all the time. But what about routing tables? So the problem that we're going to underscore today is that when we have a whole bunch of class full, or now we're going to increase the number of networks because we just subnetted, right? If I have a class C and I created 4 subnets, that's 4 routing table entries. And so if you take the number of possible class full addresses and then you subnetted all of those and you put those into routing tables, the routing tables get enormous, and they were big already because of just class full addressing. So what we're going to do today is go the other way with our mask, and we're going to address those poor, suffering routing tables. Now, just to give you an idea, this is core internet routing tables, and these are the BGP, the Border Gateway Protocol routing tables, and these are tracked by Podaroo.net. The upper number here is 1 million entries, and you can see the growth of routing table entries, and this is coming up on 2024 data. So this is pretty accurate, it's pretty up to date, and what this is telling us is that core internet routers have routing table sizes that are nearly 1 million. What this also means is that if you got a router that's processing millions of packets per second, it has to sort through, potentially, 1 million entries. It's not exactly how it works, but the more entries you have, the slower this gets. And so again, what we want to do is figure out a way to collapse the number of entries that we have. So, fooling around with the mask. Previously, we said, if I've got the problems of a growing network, too much traffic, I've got security issues that I want to narrow down, right? I want to handle broadcast traffic, all of that, we chop up the network space. We're going to do the opposite. We're going to increase the size of the network address space. And what that does is immediately reduces the size of the routing tables. And I'll show you exactly how that works here in a minute. So where previously we changed the bits in the host portion, that is where the zeros start off, and we turn those into ones, what we're now going to do is change the network portion of the mask. And that's where we see ones, and what we're going to do is convert those binary ones to zeros. And that's how we aggregate routes together. So the keyword and tricky phrases to sort of glue together here, we've got supernetting, aggregation, and route summarization. These are all related terms or even synonyms. So let's do some examples. Now to get us started, let's ask the question, what network is this node on? And if I ask you that question, you should ask me a question first. You should say, well, wait a minute, Hartpence, what's the mask? And so because this is a class C, I might say something like this, right? 255, 255, 255.0. And then you would say, well, cool, what I'm going to do is I'm going to do the ANDing process. Maybe we'll make it look like a little bit of division, like that. And you would AND this, and you would say, aha, well, the answer that I get back after ANDing is that. But now what happens if I change the host portion to this? And remember that, okay, what we're doing here is we were at all zeros in the last octet, right? And what I'm doing is I'm saying I'm going to change this one to a 1. Well, what does that do when we do the ANDing process? Well, it doesn't actually do anything in this particular case because 99 ANDed with this value still gives me a .0, even though the address space is shrunk. So what happened was this network was 256 possible values. Now it's 128. But then I want to do more subnets, right? And so I do something like this. And then all of a sudden what we find out is that the network to which this host belongs is now 210, 205, 200.64. Now, if you didn't follow that, I advise you to go back and take a look at the subnetting video because they do all the binary there. What we're going to do today is we're going to say, well, okay, that's cool. So we go back to this. And now I'm going to start manipulating the network portion. And so what I'm going to do is take a look at this thing right here and maybe change the value to something like this, which means that I now have to take a look at the 2 octets in the mask. So now where previously I might have done this, like that, we'll sort of separate them out, make it clear. What I just did is I'm going to change one of the 1s into a 0, and that's what gives me 255, 255, 254. And so now what is the impact of this? Well, for that we have to look right here and here. We have to take a look at both of those. So let's do the example in all binary. Okay. So when we have 210, 205, so maybe I'll do it this way, 210, 205, and I'm trying to do this in real time so that you all can, sort of follow along with exactly how this works. So 210, oh my goodness, what is that? Well, 128, 192, well, what do I need? I need another 20 or so. So if I did this, this would be 224. I don't want to do that. So 192 and 16. Oh, that might work. So 192 plus 16, 208. And so we got to keep going. So we do, well, 8's not going to work, 4's not going to work, 2 will work. So that should do it for us. And we'll do this now, 205. Okay, so that's just 5 less. I think we can do that. Well, now this 208 is not going to work, right? So we can't do that. So now we got 192. We want to get to 205. How do we do that? We need 13 more. And so we go 8, maybe 4, like that. Okay, so all that I'm doing, remember, is we're remembering our powers of 2. So this is 192. That's 32, 16. 192 plus 8 gives me 200, and that gives me 205. Okay, now the 200 is pretty easy because that's it's so derivative. Like that. Let's see if we get our binary. Okay, now we'll do the 99, but that's quickly going to fall by the wayside here. So that's 96, 16, 8, 4, and then 3. All right, so that should do it for that. All right, we're also going to remember our mask, right? So our original mask looks like this. Let's see that, 8, 8, there we go. Okay, so when we do the ANDing process right here, right, we know that because it's a class full, anything that I put there doesn't matter. It gets ANDed with a 0, and then I bring it on down. Okay? Now, what I just did was I manipulated this bit right here. And maybe what we'll do is we will separate that thing out, and we'll show where we changed it again. Okay. So now we might have said previously this was our subnetting field. Now we're going to call it our supernetting field or our aggregation field. And so now what this means is it doesn't matter what I put there. Now previously the range was, well, maybe we'll put that up here, right? Say range was 0 to 255. And now the question is, what's the range of addresses? Well, if we just got done saying that where there's zeros, it doesn't matter what I put there, it also means that it doesn't matter what I put in that particular binary position either. So now the range of possible addresses just changed. In fact, it doubled because it's a power of 2. Now there's no real easy way to show you this other than to say, let's do some examples and we will prove to ourselves what the range of possible addresses is, and then we'll take a look at the impact. So what I'm going to do here is say, all right, again, what's the network upon which this node sits? And it's still, right, we do the ANDing like that. which means that it's still 210.205.200.0. Okay, it's still that value because when I do the ANDing. But let me ask you a different question. What if I do this? I'm going to copy the whole thing, but what I'm going to do is I'm going to change this to 201, which means that I just changed this value to 201, which also means that when I bring this down, this is still a 0. So now 210.205.201.99 is also on the 210.205.200.0 network, which means that when I do the ANDing process, the range of addresses has now changed to at least be twice the size of the address space. Now, let's do an example on either side of that. Let's do this one. I'm going to try and keep them all on the same page here. So now let's do 199. Well, what does 199 look like in binary? Well, it's 192, like this. And we'll keep our columns. Oops, like that. Make sure I get my ones and my columns correct here. My eyeballs are playing tricks on me because of this separation here. All right, so it's 192 plus 7. Okay, now when we do the ANDing here, maybe what I'll do is I'll just change this particular example. So what do we get? We get 210, looking good so far, 205, but what does this ANDing process give me? Well, it doesn't matter what I put there, but all of a sudden I got to bring down not this one, right? But these two I got to bring down. Whoops. These two I got to bring down. Which means that suddenly this is now not 200. It is now 198.0. Okay, well, what happens if we go to 202? We make this 202. All right, so that looks like that, I think. 192, 202, yep. So now the binary pattern looks like this down here when we bring it down. So now this becomes, well, 202. So what this seems to say is that 202 is out of bounds and 199 is out of bounds. So now what we can do is get rid of all of these. So if you want to pause the video, right, take a look what I did there. So now our new range is 210, 205, 200.0 to 210, 205, 201.255, or 512 possible addresses and 510 usable. Just for fun then, we would say, well, maybe what would a router be? So if that's the range of possible hosts, a router might be sitting at, 210, 205, 201.254, something like that. Okay, what would the new mask be again? The new mask would be 255, 255, 254.0. The key is in the binary. So what this would mean from a routing table perspective is that these two entries, if I had an entry for the 210, 205, 200 network, right, this one, and an entry, whoops, let's fix this. Oh no, we're okay. And we fixed this, and we had an entry for the 210, 205, 201 network. Let's put it this way. So routing table change. We had the 210, 205, 200.0/24, CIDR notation, and the 210, 205, 201.0/24. What we are saying is that both of these could be aggregated together into the 210, 205, 200, whoops, 200.0/23. So the router now can collapse its routing table by one entry. And again, the key is in the binary. And so if we start to take a look at this, what we're aiming for is the patterns that are in the binary. So let's take a look at that. So in our case, we were interested in that third octet. So again, we're starting with 210, 205, 200.0. And we'll do the binary, we'll put the binary down there for that one again. Now all the action is going to happen in this third octet. But for right now, let's just take a look at the binary patterns. So I'm going to take a look at a couple above and below that. Okay, through the miracle of editing, we've fast forwarded a little bit, and here's a table of binaries. So what we have is a whole bunch of Class C networks on this side, and oops, let's start off here with 255, and then I've got the masks down here, and we're going to manipulate the binary. The key to subnetting and supernetting is to take a look at the binary and see what patterns match. Now we know in the classful address space, it's all zeros here, so it doesn't matter what I put in a Class C last octet. All right. So now what I'm going to do is start manipulating the mask here, and I'm going to say .0. And now I'm going to separate all of these because this is suddenly the bit that I care about. The one bit that I care about, or the one bit that I say, well, actually, I don't care what's there. And you can see we've got alternating ones and zeros, but that's not really the point. In order to supernet something together, the binary pattern to the left has to match the binary pattern of the network that we want to aggregate. And so if we start taking a look at this binary pattern, we can say, well, that's 11000001. We take a look at the next pattern, it doesn't match. But these two match. So I might say, well, I could aggregate these two together. Whoops, let's do it this way. I could aggregate those two together because their binary patterns match. That is to say, when I take a look at how the ANDing process would go, then suddenly these two could be aggregated together. And any result that was ANDed with these zeros now, the 9 zeros now, would give me the same value. And so the range of hosts would be 210, 205, 196 to 210, 205, 197.255. Now if I take a look at the binary pattern here, oh look, these match, but they don't match the one above it. So I could aggregate these two together, and the binary pattern will be 210, 205, 198, whoops, dot 0. Oops, I forgot my dot 0 up there. Dot 0 to 210, 205, 199.255. Okay, so now I take a look at 200 and 201. This is the example that we did previously. We know that these already match, so I could match those two binary patterns, right? And the range here is 200, 201. And the same thing goes here. The 202 to 203. And then look, we've got another match here. And that would be 204 to 205. Okay, if we did 206, what we would find out is that this value would be a 1, and it wouldn't match. So we couldn't aggregate 206 together. Okay. Well, we're going to get rid of all of our bold here. And now we're going to say, well, what happens if I change this not to 255, 255, 254, but what if I steal another bit from the networking portion and I say 252? Now what that means is that I have to change this one to a 0, and now I care about, right, these 2 bits. Like that. All right, so now what are the patterns that match? Well, there's our pattern. That doesn't match. Oh, let me say this too. Right, we stole 1 bit. How many possibilities are in 1 bit? 2. So that means we aggregated previously 2 Class C networks together. Right? Now we're going to steal 2 bits. How many possibilities are in 2 bits? Well, there are 4. So now the spoiler is that we're going to aggregate or supernet 4 networks together. So now we're looking at the patterns and we go, oh, what are the patterns that I care about? There they all are. Okay, so this value is 196, but now I find out that because I don't care what these other ones, look at it, there it is, 0, whoops, right, 0, 0 in the supernet field, 0, 1, 1, 0, and 1, 1, but because my field is zeros here, doggone it, word, there we go. Because it's zeros, I don't care what's in those binary patterns. So now the networks that can be aggregated together, well, there's 4 of them, right? And so now my address space is actually this. And I can get rid of this one. So my new routing table, which previously had 210, 205, 200, well, let's see, 196 maybe, 196.0. It would have, right, previously you would have had 4 entries in the routing table for those 4. They all would have been /24s. And now we can say that we can convert all of these to 210, 205, 196.0 slash what? Well, we stole 2 bits away from the networking portion /22, which also means that these 4 would also be aggregated together. Take a look at the binary patterns here. 1100, 1101. Whoops, wrong octet. 110010. So all 4 of these share the same thing. And so this range would actually expand to be 4 Class Cs. Now, if we take a look at what happens right here, right? Suddenly we've got, instead of 1, 0, we've got 1, 1 in the binary. So these guys are out of the pool. So this aggregation would actually go to 207 if we included those. Okay? So that also means that the address space, the range then, right? We have the range. What might be a router here? So maybe a router would be 210, 205, 199.254. And all hosts, because now we're at 1024 possible hosts, right? 1024, oops, 1024 possible, 1022 usable, okay? Where this is the supernet ID, this is the supernet's broadcast address, and here's a router I might use. Now again, how do we know that? Well, if I did the ANDing for any of these addresses with this mask, they would all get the same value. They would all get 210, 205, 196.0. And so that is the way that you would take a look at a supernetting problem. We'll do one more here with the Class Cs. Let's say that now I change this to, well, if we steal one more bit, right? So this is the 4 place, right? That would be 4. So I'm going to subtract 4 from this. So I'm going to say 248 now, which means that I'm going to convert this to a 0. Just to make it really clear where we are. Word, stop trying to figure out what I want to do. There we go, like that. So now what we're going to do is say, well, I don't care what you did in 3 bits. Right? So now it doesn't matter what any of these values are. So we'll go back to like this. So now again, I'm looking for this binary pattern right here. There it is again. There it is again. There it is again. Oh, wait a minute. Whoops. Okay. And now it changes. Now it changes. So now what I'm doing is I'm finding out that, well, what would the network actually be for these hosts here? Is it 196 now? No, it's not. It's actually 192 to 199. And so what I'm now doing is I'm aggregating 8 networks together. Now to prove that, we might as well add a couple of lines here. And I'm going to, we'll do an actual binary example. I'll try to keep a bunch of stuff on the same page here, but now this would be 206, 207, and 208. Well, what does 206 look like? Looks like this, right? 207 and 208. Make sure I got that right. 192 plus 16 is 208. Okay, that looks good. Well, here we go to 11001, and that pattern is consistent all the way down to here, where it now changes. So what that means is that all of these networks have the same binary pattern to the left of the bits that I stole. So that means 1, 2, 3, 4, 5, 6, 7, 8 networks got supernetted or aggregated together. So we can get rid of this, right? And we can now say that this would go all the way to 207. Whoops. 207. 207. There we go. 207.255. And again, how would we know that? Because look, I've got more zeros down here in my mask. So it doesn't matter what I put in these now 11 bits. What would this new mask be? So let's do this. Well, we'll go ahead and put it over here since we can see it. Our new mask is 255, 255, 248.0. Or we would say /21. A router, right, you can probably guess, would sit at the highest usable. So we would say 210, 205, 207.254, right? And I might also say that, our possible hosts, well, we just glued together 8 class Cs. So how many is that? Well, if we do powers of 2, right, we did 512, 1024, now we're at 2048. 2048 possible addresses, which means that our usable addresses are 2046. Try that again. All right, evidently I'm getting tired. Okay, so that means that if we were to glue all of these together in a routing table entry, then one routing table entry where previously we might have had, 8, it would be, 210, 205, 200.0/24 all the way to 210, 205, 207.0/24. So that's 8 routing table entries. We would change all of these to 1, and we would say 210, 205, 200.0/21. So that is the new routing table entry, and we would collapse all of these together. So that's how it's done on the binary side. Now, if we drew a topology, we would just say, well, all of these networks would now be reached with one routing table entry. So there we go. Now, we're getting long on time here, so let's just do a quick Class B example.
Well, good gracious, since we are getting so long on time, I am going to cut this video right here. Class B will be in part 2 of this same video. And whether you're in part 1 or part 2, may those packets always reach their destinations.